In this lecture, we will discuss how to determine the electrical axis in the frontal plane. The electrical axis represents the general flow of electrical impulses through the heart, from the sinus node to the Purkinje fibers. In other words, it is the direction of the resultant vector. So if you look here, we have all these small vectors within the heart, okay, and all of them, if you were to add them up, they would all have this direction and magnitude. They'd be heading this way, okay, where this big arrow is heading towards this direction, leftward and inferiorly, okay? So that's the main vector in our QRS or ventricular vector that we'll look at. Now, if you wanted to find the XY axis or the axis in the frontal plane, you would use the limb leads. And if you wanted to find the Z axis, you would use the precordial leads. Here we're going to look at how to find the axis in the frontal plane. So we're going to focus on the limb leads, specifically leads 1, 2, and AVF. We will also focus on the ventricular axis or the QRS axis for our teaching purposes. You can also apply these same principles to other waves and segments on the EKG. Okay, now before we go any further, let's briefly review vectors and how their direction affects what manifests on the EKG. In general, if a QRS complex is positive in a lead, it suggests that the vector is traveling towards that lead and the axis is roughly in the same direction. Okay, so again, we're dealing with our depolarization waves, a positive wave. If you look here, we have our vector heading towards the lead and towards that direction, and therefore we see a positively deflected, okay, QRS complex. If the QRS complex is negative in a lead, it suggests that the vector is traveling away from that lead and the axis is roughly in the opposite direction. Okay, so now we have our vector traveling in this way away from our lead, and because of that, we have a negatively deflected QRS complex. And if the QRS complex is isoelectric or biphasic, it suggests that the vector is traveling perpendicular to the lead and the axis is roughly perpendicular or 90 degrees to that lead. Okay, so again, now we have the vector heading in this direction. Our lead is right here, so this is 90 degrees to it, and because of that, we have this isoelectric. Right, as it heads towards our lead, it sees a positive deflection, and as it heads away from it, it sees that negative deflection. So because of that, we see this isoelectric or biphasic, right, that both sides are equal in amplitude, okay, and that's because it's perpendicular to that lead. All right, so what is generally considered normal and abnormal for ventricular or QRS axis? Well, if you look here, we have our normal axis lies between -30 and +105. So where is that? Okay, well, for our references, this is considered 0 degrees. This is considered +90 degrees. This would be plus or minus 180 degrees. Okay, and this is -90 degrees. All right, and I've laid it out here for you to easily see. So here in green, from -30 degrees to +105 degrees, this whole area is considered normal ventricular axis. Then we have leftward axis or left axis deviation, and that's from -30 to -90. So here's -30, here's -90. This here in red is considered a leftward axis, leftward shift or left axis deviation. Then we have right axis deviation, which is from +105, okay, up until this positive 180 degrees. This area here is considered right axis or a rightward axis shift, and that's that blue area. And then we have extreme axis deviation, okay, sometimes referred to as no man's land, between this -90 right here and -180, okay. So that there in yellow is our extreme axis deviation. It's rare, but sometimes can be seen. Now we can have something called indeterminate axis, okay, and this can occur in a few different ways, but one way is if we have leads 1, 2, and AVF, the leads we'll focus on, if they're all isoelectric. That means we cannot determine the actual axis because there's no vector that's actually heading more strongly towards one of those leads, okay. So imagine that we have this here, this isoelectric complex in leads 1, 2, and AVF, we call that an indeterminate axis, okay, meaning we cannot determine what the actual axis here. Now let's use leads 1 and AVF to look at how the axis can change based on if the QRS complex is positive or negative in a lead, okay. So let's look first at, let's use this one here, Okay, we'll look at normal axis. Okay, and you can think of it as a quadrant system. Imagine this is normal. Okay, this is a leftward axis, right? Notice that some of the normal axis sits here. Okay, so there's something else we'll have to consider. This would be the rightward axis, and this is the extreme axis. Okay, now what we're going to look here is in this quadrant, first at the normal axis. Okay, and what does that mean? Well, if you look here at the ones in blue, those vectors are heading towards lead 1. Okay, and lead 1 sits here, lead AVF sits at positive 90, and then we'll look at lead 2 that sits here at positive 60. Okay, that's lead 2. All right, so notice here in lead 1 we have a positive complex heading towards it. Okay, so our vectors are heading in that direction. So what we would do is draw a vector going towards lead 1. Okay, then if you look at lead AVF, this is also a positive upright vector, so the vectors are heading towards AVF, okay, and that means our axis sits somewhere in between there. In between there is our normal axis range, okay. Now if we go to the left of that, all right, let's erase some of this here so you can, okay. So if we go to this one, now we're looking at a complex that has a negative deflection in lead 1, okay, and because it's negatively deflected, this is the positive end of lead 1. We're going the opposite direction towards this one, okay. Then we're going to look at AVF. This is a positive deflection in AVF. Remember, these are the positive. Remember, the positive sides of the leads are what get the name, okay. So if the positive end of AVF is here, we're going to head towards it. Okay, that means our axis lies somewhere in this range, which is our rightward axis. Okay, and then if we go up to this one right here, we can see that we have a positive complex in lead 1. Okay, so positive complex in lead 1 means we're going to head in this direction. And then if we look at AVF, this is negative. Okay, so that means going in this direction away from the positive end of AVF puts us in this region. Okay, and because of now we're in this region, you may wonder, are we actually in that normal range, or are we in this actually pathological leftward axis? Okay, and how do we determine that? Well, we determine it by looking at lead 2. Okay, and what we do here is because lead 2 sits at positive 60, we make a line that's perpendicular to it, okay, that actually lies here at negative 30 degrees, okay, and if lead 2 is positive, it'll be heading on this side, so it'll lie in that normal region. If lead 2 is negative, it'll lie on this region and in that leftward axis zone, okay, so that's something else to consider. Now we have this last case where there's extreme axis deviation, okay. In this case, notice we have a negative in lead 1. So we're going to head away from that, and then if we look at AVF is also negative, so it head away from AVF, and it'll put us in this region here. So that's, again, an extreme axis. Another that's rare, but just something to be aware of, okay? So hopefully this is starting to make sense. Let's go through a real example here. Now take a look at the 6 limb leads here in the upper right. If you want, you can pause the video and try it for yourself, and then restart the video when you're ready. All right, let's go through this, okay? So first, let's erase this so we can have a clean slate to work on. So, okay, let's label our stuff here. So this is 0 degrees, and that's where lead 1, the positive end, sits. This is positive 90 degrees, okay, where the positive end of AVF sits. This is plus or minus 180 degrees, negative 90 degrees, okay. And then remember, we have lead 2 that sits here at positive 60 degrees, okay. So this is the same approach you can use when you're finding the axis just in regular practice. So what we're going to do is we can take a look at lead 1, okay, and notice that lead 1 has these positive complexes, okay, so we're going to head towards lead 1, all right, and then we're going to look at AVF. So here's lead AVF, and notice that AVF has these mostly negative complexes, okay? So AVF's positive end is here, we're going to head away. That puts us in this region here. And remember, that means we're either lying in that region that's normal, which would be this area here, where negative 30 sits, or it could be in that leftward axis zone, which is in this region. And we said what we have to do in these cases is look at lead 2. Okay, so here's lead 2, and look at lead 2. It is actually mostly negative when you compare it to its positive portion, okay? The amplitude of the negative part is more so than the positive, okay? So this is slightly negative, okay? And because of that, we said if it's positive, it'd be on this end, heading towards the positive end of lead 2. If it was negative, it'd be over here. So because it's negative, that puts us in this region here, all right? And the actual axis here was negative 42 degrees. So what does that mean? That means the axis lied somewhere about right here, right? And that should make sense because we said it was only slightly negative, so just slightly beyond the negative portion. All right, lastly, there's an algorithm here I put together. It may help you. Some people like these. So again, what I suggest is you look at lead 1, okay? So imagine this, we're looking at lead 1. Is it positive? Yes. So if it's positive, then look at lead 2, okay? And if it's is it negative or positive in lead 2? In this case, it was negative, so that puts us in that leftward axis range. If it was positive, we'd know automatically it's normal axis. So you can think lead 1 and 2, both positive, normal, okay? And then if lead 1 is negative, then you have to consider AVF. Okay, if lead AVF is positive, you would have a rightward axis. If you have negative in lead AVF, that would be an extreme axis. Okay, that's just something that may help you. I think it's pretty easy just drawing this out and doing it yourself. Okay, it should come second nature pretty soon. All right, let's briefly review what we discussed before we end. So the electrical axis represents the general flow of electrical impulses through the heart from the sinus node to the Purkinje fibers. We said this is the direction of that resultant vector, this here, okay? And we're talking about the axis in the frontal plane, the XY axis, so we use these limb leads, okay? When we discuss the Z axis, we'll use the precordial leads, different axis, but we're focused here on this XY axis. We talked about specifically the ventricular axis, and we use these methods to find it, okay, what was normal and abnormal, but you can use these same concepts for different waves, the P wave, the T wave, as well as segments, such as like the ST segment, okay? Now, the QRS axis, we said normal, it lies between negative 30 and positive 105 degrees. Leftward axis is between negative 30 and negative 90 degrees. A rightward axis shift is between positive 105 and positive 180 degrees. And then we had that extreme axis between negative 90 and negative 180 degrees. We also mentioned this indeterminate axis. If we cannot define the axis, meaning is it isoelectric in those leads, then we call that indeterminate. All right, and then we went through all these methods in the examples, review them, but hopefully this is starting to make sense. Well, that's the end of this lecture. We discussed how to determine the electrical axis in the frontal plane. I hope you learned something.